Hess from Dortmund, who's going to knot some strings and flavour some leptons.
Okay, so this is about an idea or an observation, not really a model, which again could relate particle physics and knots. And it's about knotted strings and leptonic flavor structure, relying on this paper here in collaboration with Tom Keppard and my student Philip Laser. And so what's leptonic flavor structure? Leptons are the electrons in the atomic shell, and the neutrinos, as you know, neutral, barely interacting, very light particles. And these neutrinos are very different from the charged leptons, the electrons, muons, tau, and the quarks. And in several respects, as I said, they are much lighter, they barely interact, and they mix very strongly. And what do I mean by they mix very strongly? Well, this is Heisenberg and Bohr here on a table with lots of beer bottles, so they had funny ideas like in quantum mechanics, a system is situated in the coherent superposition of all possible states, meaning cats are simultaneously dead and alive, and neutrinos are simultaneously in different mass eigenstates. So that means the neutrino state, which is actually interacting in a particle physics reaction, is a superposition of different neutrino states you can assign masses to. And if you create a neutrino in an interaction, then it propagates as a superposition of these mass eigenstates. So you can write your neutrino flavor eigenstate, the interacting eigenstate, as the sum of a product of a matrix element of this mixing matrix here and the corresponding stage nu I, which you can assign masses to. And then you just look how the matrix element, when you create, for example, an electron neutrino at one point in space, and you let it evolve accordingly, and then what's the probability to detect a muon neutrino at another point. So you just square the matrix element, and it's a simple exercise to find out that this goes like sine squared 2 times of this mixing angle, parametrizing this mixing matrix, and an oscillatory term depending on the differences of mass squares. And then you can compare that essentially to what experimentalists have measured. And this here is a summary of solar neutrino oscillations. So this process is called neutrino oscillations. You create a neutrino in a flavor eigenstate. This propagates as a superposition of mass eigenstates, and at a certain point you have a probability to detect another flavor. And you can look at neutrinos from different sources. From solar neutrinos, well, there are some subtleties according to matter effects, but anyway, so I don't want to go into these details. You can look at neutrinos created in the atmosphere. You can look at neutrinos created in reactors. And this is a summary of all these results. On the x-axis, there's tan squared of this mixing angle. On the y-axis, there's the difference in mass squareds. And what you see here is that both solar neutrinos as well as atmospheric neutrinos, they show pretty strong mixing. We have large mixing for solar neutrinos and maximal or almost maximal mixing for atmospheric neutrinos. So if you look at this mixing matrix parameterized by this angle here, it has this approximate tri-bimaximal form, it is called, with one maximal angle, one large angle, and one rather small angle, which nevertheless is finite, as we know, since April of 2012. So this is way different from the way quarks behave. Quarks also have mixing between flavors, but the mixing in the quark sector, they are parameterized by the small angle, the Cabibbo angle theta, Cabibbo, and so this is an important question: why neutrinos are so different in this respect from quarks. So how do people try to explain that? Well, the standard way is, so this is once more the point. We have large maximum mixing in the lepton sector versus small mixing in the quark sector. And if you look at the mass hierarchies also, we have mild mass hierarchies in the lepton sector versus strong hierarchies between the masses in the quark sector. And typically people invoke some flavor symmetry, typically one discrete symmetry group where they assign the particles to representations and then look at the corresponding Lagrangian, break it in some way to explain these patterns. And several flavor groups have been studied, and this definitely is an interesting and attractive way to explain these patterns. But as we will see, there's lots of arbitrariness involved. And some other people have said, well, maybe it's not due to symmetry, maybe it's just anarchy. Maybe masses and mixings are just random numbers, and also they get pretty good fits. And the question I want to address in this talk is there maybe a third possibility, that it's neither a flavor symmetry nor anarchy? And this once more looks at these flavor models. And this was before this small mixing angle, theta 1,3, was measured in spring last year. And this was a study by Albright, Chen, and Rodo Johann, who looked at the prediction for the small mixing angle and the number of models, different flavor models, who predict it. And as you see, well, there are some more models predicting a large mixing angle here, but maybe this is wishful thinking, since theorists always like to predict what experimentalists can confirm in the near future. In any case, you see that it is not very clear where this mixing angle lies. And this is even more clear in this plot here, which is from a study of Paratu and Vingeta, where all three mixing angles were looked at, and they scanned over 1,048 groups based on A4 times some other group, and actually on 41,000 models. And what you see is that these predictions essentially span the whole parameter space. So what we have here in this flavor symmetry approach, although it is attractive, there's a huge variety of models, and the predictions span a large part of the parameter space. So I think this strongly motivates to search for new tests of flavor symmetry. For example, you can look at the Higgs sector at the LHC and try to discriminate these flavor symmetries, but this is a different story. Or you can look for alternatives of flavor symmetry. And that's what I want to talk about. So the question is, what are these flavor symmetries actually doing? And the major achievement of these flavor models is that they motivate to generate mass matrix entries. So what is this matrix here? This essentially is just a matrix with three masses, M1, M2, M3, diagonal matrix, and then you sandwich it between these mixing matrices here, which come from experiment. And then what you get is a structure like this here, and what you see is you have several y's here, x plus y and y minus, well, okay, it has to be symmetric. But so several entries of this matrix are identical. So the question is, okay, this might be due to flavor symmetry. Maybe it's just random numbers. Or are they maybe even other phenomena in nature with close numbers? And that's my point here, the connection to knots. So, so these are possible knots, tightly knotted knots. Some other speakers talked about it already, like Tom Keppard. So this is a 3-1 knot, three crossings, one component. This is the 3-2-1 link, three crossings, two components, and this is an index. And so you have lots of different possibilities to construct these knots, and then you can put down these numbers, also showed by Tom Keppard already, and as Tom already had said, is if you go to higher numbers of crossings, there are more and more possible knots you can construct. And what does it mean? Well, this means that if you look at such a table and you go to a reasonably high number of crossings, you find lots of numbers which lie very close to each other. So this is just what we want to explain flavor structure. We want to have numbers which are very close to each other. And the question is, well, maybe this is just numerology, but maybe there's some deeper meaning. And so this is again from the paper of Roman Buni and Tom Keppard, where they looked at a model where they assumed that the knot length is proportional to the knot energy, which they got out of some flux tube model. And as Tom showed already, they get very nice fits to some J++ non-QQ states, which could be interpreted as glue balls. So back to neutrinos. How do we generate neutrino masses? The most popular model to generate neutrino masses is the seesaw mechanism. And the seesaw mechanism starts with the fact that in the standard model, the neutrino mass is 0, since you don't have a right-handed neutrino. A mass is always a conversion of a left-handed state into a right-handed state. So, of course, what you can do is you just add a right-handed neutrino to your standard model. Then you can transform your left-handed doublet into a right-handed singlet, and you couple to the Higgs, which is also a doublet. So the whole thing is invariant under the gauge group of the standard model. But now you have a right-handed neutrino which has no quantum numbers under your standard model gauge group in your theory. So it's allowed to write down a Majorana mass which transforms the right-handed neutrino into the left-handed antineutrino, a mass which connects neutrino and antineutrino. And since both are singlets under the standard model gauge group, you don't need any Higgs to write down this mass. So this mass can be very large, way larger than the masses of the other particles. And then if you glue these two different masses together, your left-handed neutrino couples to the Higgs, you get a right-handed neutrino. You go over to the left-handed antineutrino, couple again to the Higgs, and you get a right-handed antineutrino. And you get an effective mass for your light left-handed neutrinos and right-handed antineutrinos, which scales like two couplings to the Higgs. So the Dirac mass squared divided over the heavy Majorana mass in the propagator here, which goes just like a quantum fluctuation. So it's suppressed with this heavy mass here. Okay, thanks. And so of course, if you have 3 generations of neutrinos now, you have a matrix of this type where you have the Dirac masses on the off diagonal and your right-handed Majorana masses on the diagonal. And then by integrating out these right-handed neutrinos, you get your mass matrix for your left-handed neutrinos in flavor space. So what's the idea now to invoke knots? Well, so it's pretty vague, admittedly, but in string theory and ADS QCD duality, glue balls, gravitons, and modulinos are open strings. And people who, for example, constructed extra-dimensional models for neutrino masses, they used extensively that right-handed neutrinos can be closed string modulinos. So maybe there's some relation between all of this, between glue balls, right-handed neutrinos, and right-handed neutrinos maybe have something to do with closed strings, and they can have non-trivial topology, and we can model this mass matrix here of these right-handed neutrinos with knot numbers. So our ansatz was, we assume that we can model this matrix with knots and links. So we put knots on the diagonal, we put links on the off diagonal, and then we just looked what happened. And So if you integrate out the right-handed neutrinos, you construct your mass matrix of the light left-handed neutrinos, then it looks like this. MK are the not entries, ML are the link entries, and then you have this matrix here where this delta 3 is this expression, and you can compare this for tri-bimaximal mixing matrix for various hierarchies. And for example, if you have a normal hierarchy, this essentially means you have one massive light neutrino, two which are essentially massless. Then your mass matrix in flavor space looks like this. And if you compare that to the matrix on the slide before, then you get these expressions here. And so if you look, for example, on these first three conditions here, then as you know, the Dirac masses, they are all at the scale of the electroweak symmetry breaking of something like 100 GeV or so. So they are of the same order of magnitude, and that means that correspondingly the MK and ML, which are defined by this parameter times some heavy scale, they have to lie close to each other. So you need here these entries which lie close to each other, and this suggests that knots and links fit better than random numbers for this specific hierarchy. What about other hierarchies? If you have inverse hierarchy, that means you have two heavy neutrinos, one massless, essentially. This type of mass matrix, this can be only solved if m tilde is 0. That means, of course, the whole matrix is 0, and this means this hierarchy is disfavored for knots and links. Similarly, if you have degenerate neutrinos where the masses are much larger than the mass squared differences, then you get the requirement that the link numbers are all 0, and this also disfavors knots and links, obviously. So then we made a numerical scan over some, how much is it? 10 million models. And what we got was an excellent fit to the data. I mean, this is not trivial since we have a non-trivial structure of this matrix. And but of course, this fit, on the other hand, is so good since we had a lot of models. So experimentalists are always confused that this chi-squared is so small. This is since we compared so many models with one pattern. Then, of course, it might be that it's just the number of models which makes it good, and we compared with random numbers, and this structure with knots and links compares favorably to random numbers. 3.1% of the models gave a good fit versus 1.6% of the models. And as we have understood analytically already, normal hierarchy is preferred both by the structure we assumed, diagonal Dirac masses as compared to the mixing coming from the right-handed sector, as well as from the knots and links spectrum. So 30 times more models fit normal hierarchy as compared to inverse hierarchy, and this is bad news for people who look for a rare nuclear decay, neutrinous double beta decay, which looks at the lepton number violating decay of 2 neutrons into 2 protons and 2 electrons, which is proportional to the light mass, and which in normal hierarchy models where the light mass is essentially 0 is suppressed. So we see here this observable for this decay, which is very small, way below the present sensitivity of experiments, which are at 0.1 electron volt or something like that, or even bigger. And this shows the mass of the lightest neutrino here. Okay, so I come to my conclusion. Hello. So there's a huge variety of flavor models based on flavor symmetries, which give neither generic predictions nor discriminators in the neutrino sector. And this strongly motivates to look first for tests of flavor symmetry, and on the other hand, for alternatives. One alternative is anarchy, just random numbers. But my point here is that symmetry and anarchy are not the only explanations for the leptonic flavor structure. This is the main point. And an example for this is if you look at seesaw models with right-handed neutrinos modeled as knotted strings, then you get an alternative to symmetry and anarchy, which also gives good fit to the data. This, of course, as I said, is not really a model. It's just an idea or an observation. We have some ideas for ultraviolet completions, like fundamental closed strings, but the question is, well, here we have zero cross-section. So the question is, do we really get finite string lengths for these knots? There might be cosmic strings. There might be flux tubes coming from some confined E8, which is a product if you break E8 times E8 prime. But these are vague ideas. The main point is we have another possibility apart from flavor symmetry and anarchy, which could give an interesting, which could explain the leptonic flavor structure. Thanks.
Okay, there's time for one quick question, but could I ask the next speaker to sort of come up and lurk? The question is back.
Yeah, I was just asking about these fundamental closed strings because they live in a higher dimensional space. So knots are topologically non-trivial. So one could probably think about knots somehow as a test of existence of higher dimensions.
Yeah, I mean, as I said, it's just vague ideas what ultraviolet completion could look like. I mean,
Mine was a vague idea.
Yeah.
The existence of higher dimensions.
Yeah.
Okay, seems to be no more questions. Let's thank Heinrich again.